of the threefold of general type. So actually, we found that this is this can be generalized to all dimensions. That means, for the first, if we consider x, which is minimal, n-fold of general type, and we assume that P m naught of x is at least 2 for some positive number m naught, and then especially we can assume that this usually phi m naught is not birational. M naught is very small usually. Small. And then, as I said, we can get induced vibration. So, so we have an induced vibration from x prime to gamma. So when this is a generic finite or birational, the image has the same dimension with the x prime, and then in this case, fiber is a point. So so in this case, I mean the volume to be exactly the number of the fiber, the number of points in the fiber. So that means so in this case, I mean the invariance of fiber to be the degree of generic degree of phi m naught. For the other cases, we can always study really the volume of the fiber. So I always denote by F is smooth fiber F. So then it's with the same technique we can get a reasonable lower bound. That means we can get such inequality. So kxn. So this is greater than or equal to some function a in terms of the volume of the canonical volume of the fiber. So this is a linear function, and times p. Then we should replace this by p m naught of x minus. Here should be the dimension of gamma. Okay, so this is we can always do this in the same way. And but for example, if we consider fourfold, so first the general member of the moving part is a threefold, and then on threefold we try to find another moving linear system, and we take a general member in this moving linear system on the threefold. Then we take another linear system. So then we can get all kind of similar inequalities. So this we didn't write them for all dimensions, but in dimension 4 we already write something. And in our paper explicit 3, actually we use we have a complete theorem dimension 4. But I would say that this one can do this in similar way. So another generalization is that if I consider x to be a Q funnel threefold. Unfortunately, for high dimension funnel varieties, we still can't do this. So Q funnel here means minus Kx is Q ample. Of course, a terminal singularity. So we can similarly use this to estimate the minus Kx cubed, which can be done similarly. So assume that we have P minus M naught X for some number. And then we get some constant. So in terms of fiber, but this is a little bit complicated than in general type case, because it's possible that in this case the fiber can be P1 or P2 or something. So the volume doesn't has any meaning. But we can find a generalized something, some volume, but it's something like log, sometimes like log general type, something. So some constant times P, but some constant in terms of the fiber. So this is some positive number. So P minus dimension phi. Okay, so this is effective. For example, we an application is that we can found a optimal lower bound for minus K x cubed. So it's well known that for Q funnel threefold with terminal singularities, we know minus K cubed is, and this is optimal. Okay, so for high dimensional funnel variety, we don't know, and this technique doesn't work. Here, it's hard to write it down with very explicit, but it depends on fiber. Anyway, we can find some cost in terms. So, well, here. Sorry. Yeah. So here in final threefold case, so M naught is 1 bit and maybe 4 something. Yeah, we have some result. Yeah. Okay. So I don't want to spend more time on this. And so another aspect is the geographic problem. So we are interested in whether we can. Yeah. So here is Kxn. So suppose we are considering minimal n-fold of general type. So we can still consider this kind of problem. So so more or less we have something here, because we have effective inequality of another type for any dimension. But as you know that for the reason even in threefold case this is not optimal. So but we have some lower bound here. But another very natural question is, can you have can you bound from from upside something here? Can you So so in surface case, because in surface case, you know that since ks square, this is 2pg minus 4, and on the other hand, this is 9 chi os, or 9 1 plus pg. Okay, so you have some upper linear expression, so Miao Kayao inequality. But unfortunately, all this doesn't hold in high dimensions. So this is so one way to do this is you simply want to know the canonical boundedness. So suppose you have you have no canonical boundedness, then there is no linear upper bound. So let me do it this way. So so what is the so-called canonical boundedness? So I would like to recall you from surface case. So on surfaces of general type, it's well known that Bouvier is the first one to study systematically study the canonical map, the geometry of canonical map. So you consider a minimal surface, and then you assume that the geometric genus is at least 2. Then you can study canonical map. And there are 2 types. So one type is that when this is generic finite. So you have a you have a map. So this is phi ks. S maps onto P. And this is general finite. So naturally, you want to know what is the degree of canonical map. Okay, the canonical bounded says that this is of course universally bounded. It's clear that because you have upper bound here, and on the other hand, you have ks squared. This is smaller than 9 1 plus pg of s. But on the other hand, it's roughly larger than d. D means this degree, and this is pg minus 2. And therefore, d is bounded. So so this is one thing. But on the other hand, you know that when this is a fiber type, okay. So in this case, you have a induced vibration f from S prime. S prime is a smooth bidirectional model of S, so that we have a vibration onto curve. So this is a canonical vibration. Canonical vibration. Okay, and then we mean that the fiber is a curve C, and of course, this GC is at least 2. Okay, again, due to the canonical boundedness, so you have from the upper side you have this upper bound, but on the other hand, other side you have some inequality of this of the Noether type. Then it's easy to see that the genus of the fiber is upper bounded. This is universally upper bounded. Smaller than something. Okay. So in general, I think it's maybe 16 is too rough, maybe. But and then Bovee says that when you consider, when you assume that the invariance of S is large enough, say 21, and then you know that the genus of the fiber is smaller than 5, 2. And Bovee constructed several family of examples with GC equals to 2 and 3. But so far, very few examples with GC equals to 4 and no example with GC equals to 5. And I think in surface case, this is still open question. And let me introduce conjecture here. So this is well known, I think. Conjecture of Xiao. So this conjecture says that assume that chi OS is large enough, then GC should be equal to 4. So I think this is still mysterious. So in threefold case, we want to study similar problems. So the similar problems means, do you have something similar to Miao Kai Yao? If you have this kind of upper side, if you have some similar inequalities like Miao Kai Yao, then maybe you can get canonical boundedness. So first, let's consider only Gorenstein minimal threefolds. Here, everything is general type. Okay. So in this case, we know that Miałka, of course, Yao. So they have such kind of inequalities. So let me say, Yao only studied canonically polarized varieties, but for all dimensions. Miałka studied minimal threefold general type. So in fact, what I'm citing here is exactly the form of Miałka. So he says that so x. So let me assume that it to be x, and then we have kx cubed is smaller than 72 chi omega x. So this is Miałka and Yao. This is inequality, and then Haken has such an inequality. So he says that chi omega x. So here we should add one more condition, that we assume that PG of x is positive. When PGX is 0, then I don't know, maybe this is not true. Because we are considering the canonical boundedness. So we can assume PGX is larger. So chi omega x is smaller than 3/2 PG. Actually, I think in general it's 2 PG of x. Okay. So therefore, we have a upper linear bounds in terms of PGX. So therefore, we have canonical boundedness. So so that's we have joint work. This joint work says that. So this is my paper with Haken. So this is in maybe 2004. Yeah. Let's say maybe 2006. I'm not sure. Oh, sorry. 2006. So we have such a theorem. Suppose X is a Gorenstein minimal, and PG of X is at least 2, and we assume that phi kx, this is of fiber type. And then we have induced vibration F from X prime to gamma. So I denote by capital F to be a smooth fiber of F. So, so there are two cases. Either F is a curve or F is a surface, right? So, yeah. So the statement should be like this. There exists two constants, K1, K2. Yeah, and then the statement is either GF when F is a curve. So this is smaller than K1. And when F is a surface, the PG of F is smaller than K2. Okay. So the interesting point is, can you find many examples? So actually, in threefold case, we now we have a lot of several new families of this kind, and the most interesting examples are those with very large GF and PGF. And so, yeah. So another flavor is that when you assume that the invariance is large enough, so can you hope that K1 and K2 are very reasonable upper bound? So let me recall you. So for example, recently we have a new new paper with my student. So let's say. So we have a yes. We have a result. Yeah. So this is with my student. Student 3. So the result is the following. When this is large enough, sorry, I am missing one. Yes, yeah. Of course, it's very explicit. Of course, it's several hundred. Yeah, several hundred. Yeah. Okay, so so our result is like this. So when PG of X is large enough, so with the same setting, same assumption, then what we can get is G of F when F is a curve, and I assume that this is of fiber type. I haven't mentioned when this is a generic finite. So when this is a fiber type, then when this is a curve, then we know that this is smaller than 91, and PG of F, this is 37. And we have examples, several family of examples, and so far the biggest invariance, number of the invariants of fiber are, so we have examples. Um, well, in our examples, the PGF can be as large as 19, and GF can be as large as 13. So this is a published paper, so it's not easy to, not difficult to find it. So let me, yeah, this is published in, I think, 2011. Pure and apply mass quarterly. So this is volume 7, number 4, maybe 11, 17. I'm not sure. Sorry, maybe 1 and 4. Okay, so 1. Okay. So this is for Gorenstein minimal threefold.
But this bound, this PQ large enough is effective as well. You can say from starting from the law. Or
of course, yeah, PG, yeah, several hundreds, something like that. Yeah, yes, yeah. So naturally, yeah, one can. Yeah, I'm not sure whether one can find new method to get more optimal, result. Okay, and on the other hand, to my interest, I think the new way to find more examples is very interesting. Yeah, it's very interesting to find new examples with fiber, with canonical, the fiber of the induced vibration, arbitrarily large. So that's interesting. And what happens to degree? Yeah, if, of course, degree is also bounded. Yeah, so this is a result of Haken. Yeah, so Haken says that if phi kx is generic finite, then the degree. So this is bounded by several hundred, but like 5, 8, 7. And then some people they found some new examples, but the degree is so far maybe it's like 16 or something. Yeah, because you have similar results in surface, and maybe I'm not sure, but some people had some new examples. And so this is for Gorenstein minimal case. In general case, if non-Gorenstein, so if in a non-Gorenstein case, so x is, if x is non-Gorenstein, and then what happens? So in threefold case, actually Haken construct the example. Examples. These examples satisfy this property. He has a family of example x, k. This is minimal threefolds of general type. Of course, k positive, and degree of phi k, sorry, I can't use small k, maybe t x t. So this is generic finite, and the degree can be arbitrarily large. Yeah. How to say? Maybe t is sorry. Maybe t can be big. Yeah, arbitrarily large. So that means universally you cannot you cannot hope that the canonical degrees are bounded. So these kind of examples already tell you that, yeah, in general, so you can't hope in high dimension. You can't hope everything like in surface. So that's different. So so next, I want to report to you some new examples on in all dimensions and yes.
Examples of Econ-Kugorenstein.
So what?
The example of Econ are not Gorenstein, you said, okay?
But this minimal. Yeah, general type and minimal.
Okay, so it's in the definition. Yeah.
Non-Gorenstein, but minimal. Okay. So in the rest of time, I want to present several new examples. Yes. Sorry.
Just guessing, I guess that the index of these x's will also go up.
No, in this case, the canonical index is 2. All singularities are 1/2.
In all the cases.
Yes. Yeah. So you cannot hope. Yeah. It's. I mean, it's. Yeah.
So the singularities are 1/2, 1, 1, 1.
Only 1/2. 1/2 singularity is terminal singularity. Yeah. Yes. Okay. So. So I will go on this story and to study any dimension and what happens to fiber type. Yeah, this is also interesting. So so this is some examples. Yeah, some new examples. So this is a joint work with Zhi Jiang. I think he's the University of Paris. Okay, so this is so what we did in the last year. So let me explain to you the simplest example. So actually, we have 3 families of these kind of examples. So and the singularity on the minimal model are all 1/2, the terminal singularities. But so these kind of varieties are canonically fibered by subvarieties, and the invariants of these fibers can be as large as possible. So let me begin with the simplest example. If I have time, I explain to you other examples. So let me write down the main statement. So our statement is the following. So we have the following statement. So let me write it as a theorem, but in fact it's supported by examples. So this is this. Yeah. So so the statement is like this: for any set of integers, say n, this is the dimension of the variety, and for any d, positive but smaller than n, and any constant, capital N, there exists non-singular projective n-fold X, so that X, so that the phi kx is of fiber type. The fiber type means the image of X under this map is smaller, strictly smaller than dimension n. So n-fold, and X is canonically fibered. By subvarieties. Say F. Here F is dimension of F is D, is D, and the geometric genus of this fiber is larger than this. Here I should say that what I mean for PGF means the PG of the smooth model of F. Okay. Yeah, this is the main statement. So so we will construct such kind of varieties like X, usually X. Sorry, I will use too many conflict symbol, but sorry, excuse me. So if I write X, N, and D, so this always means that here I mean X is non-singular in the statement, but in the example from now on, when I say X, N, D, so that's an example with minimal, so means minimal projective n-fold X with terminal singularity. Terminal singularities, and